Hello everyone, welcome back to Pre-Cal. So this lesson is going to be building upon what you did in the last two video lessons that you have done or begun in this new unit of Pre-Cal. So you've done some review from AAF with polynomials and then focused in on dividing, right, and dividing polynomials and all of that fun stuff. So what we're going to focus on this lesson is the rational root theorem, which is going to be brand new to us. You guys did not do this last year. It is super new to us, and it's just a way to take the polynomial and figure out possible solutions without ever without graphing it or just plugging in a ton of numbers. So when you guys dealt with polynomials last year, we either had you turn to a calculator to find one solution and then maybe use synthetic division or long division to reduce it to a quadratic and factor, use the quadratic formula, or we would give you one, right? Or we would give you several different ones and you would plug them in. So you're going to use the rational root theorem in order to actually come up with these on your own. So where you don't need a calculator necessarily to develop them and to think through them. So that will be the rational root theorem, and that's what we're going to look at right now. So the rational root theorem. Let P and Q be integers that share no common factor. Okay, so we're not going to be able to simplify because they don't share a common factor. All rational roots of a polynomial, f of x, will be of this form. So rational roots, so all the possible solutions, all the possible roots, and I'm saying possible, are going to be of this form. X is P over Q, where P evenly divides by the polynomial's constant term. So when I'm saying evenly divides, it's a factor, right? So like it is a factor of the constant term of a polynomial, and Q evenly divides by the polynomial's leading coefficient. So they're going to be written in this form. X is a rational root, P over Q. Constant over leading coefficient, or factor of the constant, factor of the leading coefficient. So right here, we're going to look at our first example. So we're going to give all the possible rational roots and then determine which ones, if any, are actual zeros. So this right here, this is P, and this is Q, right? So check this out. They share no common factors. So I could say I've got 3 and I've got 1, right? Those divide evenly. I'm going to have plus and minus both of them. And then for 4, I've got 4. What else divides evenly by 4? 2, 1, right? So this is all of them. I mean, if you wanted to list them out differently, I could have plus or minus 3/4. This is really what it means. I could have plus or minus 3/2. These are possible rational roots. Plus or minus 3, right? 3 over 1. Plus or minus 1/4. Plus or minus 1/2. Plus or minus 1. Right? There's a lot of options. Right? This would be a lot for you to sit there and go through. But you could then go ahead and plug each one of these in to see which one is going to result in us getting 0, right? Which one is going to actually be a 0? The other thing that we could do is we could use synthetic division, right? So let's say I wanted to check -1, right? And I could say 4, -2, 1, -3. 4, this would be -4. This would be -6. This would be 6, 7, -7. Oh, I know -1 is not a possible solution. So let me go back. Let me try 1. Right? Oh, this makes it a +4, which makes this, what, 2? Yeah. Oh, check this out. It's 2, which would make this 3, which would make this 3, and oh my goodness, that makes this 0. Right? So that means 1 is a possible 0 of this, and you could check the other ones to figure out if any of the other ones are as well. And looking at a graph on Desmos or on your graphing calculator of this to see what it actually looks like and confirm it is a really great way to check your work as you're developing an understanding of this. So also using the rational root theorem here, I want you to think about, why do we know, without ever even like picking up a calculator or trying to solve anything or doing any real algebra here, how do we know that x is not 1/5 for this equation right here, this polynomial, right? How do we know right away, not using synthetic division, not substitution, just right away, using the rational root theorem? Rational root theorem, right? If this is the way they should be expressed, I should be able to take P and Q and all my possible rational roots, plus or minus 2, plus or minus 1, plus or minus 3, plus or minus 1. That's not an option, right? 5, 3 is not divisible by 5. Or 5 is not divisible by 3, right? That's not, like, by the rational root theorem, this cannot be 1. These are my only options, right? 5 is not a factor of 3. Think about it like that. So building on this, we're gonna see what our friend Descartes has done for us. So this is René Descartes. He's French. René, R-E-N-E, Descartes. Maybe you've heard of it. So we're going to look at Descartes' rule of signs for polynomials. So we have a polynomial again, f of x, and it's going to be written in standard form. What this is going to tell us is how many positive or negative zeros you could have, right? So we could use this alongside the rational root theorem to really work towards solving and really understanding like how many solutions and why those solutions are there. So the number of positive real zeros of a polynomial f of x is equal to the number of variations in sign of f of x. So the number of times it switches between positive and negative as you go down. So it's got to be written in standard form. That's important. Or less by an even integer, right? So if it switches signs 12 times, it could be 12, it could be 10, it could be like the number of positive real solutions, it could be 12, 10, 8, 6, 4, 2, 0, right? If it was 3, it could be 3, it could be 1, less by an even integer. The number of negative real zeros is equal to the number of variations in sign of f of negative x. So you're substituting in that negative x, or less by an even integer as well. Right? You also know how many solutions a polynomial has. How? By the degree of the leading coefficient, right? By the highest power, the largest exponent. So how many positive and negative real roots could there be for f of x? So here's f of x, and I've already done the work for you of f of negative x here to help out a little bit. So let's see, how many times does this change sign? 1, 2. Therefore, so I'm looking at f of x here, and here I'm looking at f of negative x. This could have 2 positive real zeros. Well, when we plugged in negative x, this was the output. How many times did it change signs? Nope. Nope. Yep. Once. Right? So I could have 2 positive and 1 negative, and no real, because there's a total of 3. I could have no positive and 1 negative. And this would have to then be, what? 2 for it to be 3. There's nothing. I can't put anything down here, I don't think. Oh, yeah. Yeah. I can't put anything there. Right? So let's take a look at the graph to figure it out. Whoa, there we go. Oh, check that out. There's just 1 negative. So which one was our lucky winner? This one. Right? So there's going to be no positive, 1 negative, and 2 non-real. The number of solutions for this for f of x here. Let's look at some more. This might be a good place for you to pause the video and try some if you haven't thought to do that already. So how many positive and negative real roots are there for f of x? So positive, we're going to go ahead and we're going to look at f of x. Negative, we're going to look at f of negative x. So let's see. How many times does this change sign? Once. There can be one positive solution. It's got to be one, right? There's no other option. It's just one. Let's go ahead and figure out what f of negative x is. Well, that's going to change. Negative 2x to the 5th. That won't. Plus 4x to the 4th. Minus 9x to the 3rd. Plus 18x squared. Plus 35x minus 70. So let's see. How many times does that change sign? 1, 2, 3, 4. There could be 4 negative and no non-real to give you a total of 5. There could be 2 negative and 2 non-real to give you a total of 5. Or there could be no negative, 1 positive, no negative, and how many non-real? It's got to be 4, right? Maybe you should graph it and see. We could even list out how many. List out possible ones. Oh, so look at that. Let's see. 2 negative, 1 positive. 2 negative, 1 positive, and there's 2 non-reals. So this one. So our last one here, not our last one, but our last one on this page is how many positive and negative roots could there be for f of x? So for the positive, and I don't love this table, but that's okay. You are switching signs 1 time, 2 times, right? So there could be 2 or there could be 9. What about if you do f of negative x? You're going to have 5x to the 4th minus 42x squared plus 49. My goodness. It's the same thing. It's an even function. 1, 2. So there could be 2 negative or no negative. So I'm missing a few here, right? So I could also have a combination of 2, 0 or 0, 2, right? So I could actually have 4 different pairings here. If it was 2 and 2, there's going to be no non-real. If it was 2 and 0, there's going to be 2 non-real. If there's 0 and 0, there's going to be 4 non-real. And if there's 0 and 2, there's going to be 2 non-real there. Let's see what this one looks like. 2 negative, 2 positive, right? It's that first one. And we could even use, then we could go and use the rational root theorem and realize that, well, plus or minus 49, plus or minus 7, plus or minus 1, over plus or minus 5, plus or minus 1. And then thinking about, can I use synthetic division or can I use substitution and use the factor theorem or the remainder theorem to figure out which one of these is a root and be able to reduce it to a quadratic, or reduce it to a cubic and then a quadratic, right? These aren't necessarily rational. These are just positive and negative, but we are going to use it coupled with that right here. So for this problem, find all real zeros of f of the function and identify each as rational or irrational. So I'm gonna start my step 1. The first thing I'm gonna do is I'm gonna use Descartes to figure out how many positive and negative solutions I could have. So positive, negative, right? Notice it's a 3rd degree polynomial. It's a cubic function. So f of x changes 1, 2 times. So I could have 2 or I could have 0. F of negative x equals negative 2x to the 3rd minus x squared plus 9x plus 9. So this just changes once. So there's going to be 1 negative, and there could either be 2 or 0 positive, which would then impact if there's any non-real zeros, which this isn't asking for. Okay, so that's step 1. That's using Descartes. Renee. Not convinced I spelled that right. My next thing I'm going to do is I'm going to use the rational root theorem, and I'm going to list off possible zeros. So I've got plus or minus 9, plus or minus 3, plus or minus 1, plus or minus 2, plus or minus 1. Right, so I've now listed them off. I could have positive or negative 9 halves, positive or negative 3 halves, positive or negative 1 half, 1, 3, 9. And then I'm going to use synthetic division to try to find one, right? And so I maybe try a few out. Maybe I try 1, right? Oh, you know what? I know I have a negative, so maybe I'm going to try out negative 3. And I've got 2, negative 1, negative 9, 9. And I go down to negative 6, negative 7. It's not going to work, is it? I know that that's not going to work. If I made this positive, would it work? What's negative 9 plus 15? It's like 15 minus 9. I don't know why I'm having trouble with that. Is 6? No, it's certainly not going to work, right? So 3 is out of the picture, right? And I can try out a few of them. Maybe I'm able to think through it in my head. And then maybe I get to, sorry, 3 halves, right? So maybe I try out 3 halves. Bring down the 2. I get a 3 there. Negative 1 plus 3 is 2. I get a 3 there. 6. So that's going to give me 8. That'll give me 9. Whoa, that's 18. I want this to be negative, don't I? Sorry. Do I want it to be negative? That's a 2. Oh, this is a negative 6. This is a negative 6. I want this to be positive. That's good. Which would make this 0. Right? And then, oh, check that out. F of 3 halves is 0. So I now have one of my solutions. I have one of my real zeros. It's a positive 1. So there's got to be one other positive, isn't there? There's going to be 3 real ones. So 3 halves is rational. And then I can go ahead, and if we now reduced it, and we've got, what is this? 2x squared plus 2x minus 6. Well, let's factor it. I'm going to factor out a 2. X squared plus x minus 3. And I'll use the quadratic formula. Negative 1 plus or minus the square root of b squared minus 4 times a times c. Right, that works. All over 2 times a, which is 2. Right, I factored out that 2 are divided by 2. Negative 1 plus or minus the square root of 1 plus 12 over 2. So my solutions are 3 halves, which is rational, and then negative 1 plus or minus the square root of 13 over 2, which is irrational. How cool. Right, so you're using so much in this, right? So like we're building stuff in from the beginning that you're adding into this. And this one had a lot that you had to try. So that's just a good one for practice. All right. So in this lesson, you got experience working with the rational root theorem and Descartes. This is a lot. This is a lot to work with. So I encourage you to practice and use some of the resources that we have on there to practice and do your homework. And then we will be talking about this the next time we see you in class. Thanks, everyone.